So I will speak in the board. I had several signs during this week that my computer would collapse, so I decided not to risk, and I would rather use the board. So I'll list here some references and some expression that might be useful in case I need it. So, as we saw in the next talk, in the previous talk by Ecole, the final output of the Bethe equations in the scaling limit were a set of quasi-momenta, which describe some Riemann surface. I already prepared because I will also use them. I don't want to draw them. So we will have some quasi-momenta describing some Riemann surface. This is what the kind of things which appear in the scaling limit of Bethe equations. And the corrections to Bethe equations are a bunch of cotangents and integral of cotangents. Now I want to think of the following question. I have some integrable model which is described in the classical limit by some Riemann surfaces. So the Riemann surfaces from the integrable models, they arrive immediately, directly, not as some classical limit. They are already there. We have some Riemann surface, and we want to understand how to semi-classically quantize. That is, I am given some equations describing the Riemann surface. They are very good for classical level. They are very elegant. It's very beautiful to be able to describe classical surfaces, classical solutions as Riemann surfaces. But I want a bit more. I want to upgrade this equation so that they also describe the semi-classical spectrum. And in doing so, I will understand how to modify them. And, of course, not surprisingly, I will find out that the modification to this equation will also be a set of cotangents and integral of cotangents, which will appear also very naturally from the quantization of these models. Of course, this is quite general. Indeed, we can apply it for any integrable model whose classical description is described by some Riemann surfaces, which often happens, as we will explain in a minute. So before, let me stress what is the key ingredient in the semi-classical quantization. And for that, let me start with one-dimensional quantum mechanics, because it will illustrate the main point of the construction. So one-dimensional quantum mechanics, I have Schrödinger equation. And let me introduce some quasi-momenta, P of x, which is simply equal to h bar over I, psi prime over psi. And now I want to understand, what do we know about this quasi-momenta, this function P of x? Well, psi is analytic, so of course P of x is some nice function, some analytic function. And this function psi, it has n zeros for the nth excited state. We know that wave functions have n zeros for the n excited state. So P has n poles when I'm thinking of the nth excited state. And the poles, they have residue h bar over I, of course. No matter, for every pole, the residue is always the same, h bar over I. So with residue alpha, which is h bar over I. This is one thing I know about P of x, some analytic function with some zeros, with some poles, and the residue is fixed. The second thing I know about P of x is that when I have very excited states, which means classical limit, what happens is the following. So Schrödinger equation for P is nothing but this Riccati equation. And what happens for a very excited state is that basically this term is negligible, and I get P is approximately equal to P classical, which I define as the usual WKB quasi-momenta that we saw today already. It's just a simple square root, the usual semi-classical momenta. So what is happening here? So what is happening is exactly the same thing Ecole described. So the real function is some function which has some poles. And let me draw the poles as lines going from one sheet to the other. So I have some function which has some poles, and I choose to draw it as lines going from one sheet to the other. But in the classical limit, my function P is some square root, is some curve, some Riemann surface. Of course, it's a bit too much to call a square root a Riemann surface, but we can. And it's just a Riemann surface going from one turning point to another turning point. So the cuts condensed into a square root cut. The roots condensed into a square root cut. Okay, so now I can understand semi-classical quantization in a very nice way. So I make the integral. Let me consider this integral. So I'm integrating. I will make the integral of P of x over 2 pi I. If I want to count the number of zeros, then I put the inverse of the residue, h bar over I. Of course, this is n. I'm just counting the number of zeros. And this, since in the classical limit p is more or less p classical, so this is more or less the integral, so dx over 2 pi h bar p classical. And this is Bohr-Sommerfeld quantization. So in this way, it's a nice way to see just Bohr-Sommerfeld quantization, which appears naturally. And what was the key ingredient to achieve the semi-classical quantization? The key ingredient, and the only ingredient indeed that we needed, was the knowledge of this residue. So this was the key ingredient. We knew what the residue is, so we could count the number of roots. So having said this, I can move to a slightly more complicated example, namely, I can move to strings in ADS5 cross S5. And so what is different there? There, Riemann surfaces appear quite naturally. They appear immediately. So how do they appear? So the key observation is the existence of some flat current A of x. So A is flat. A is flat, it means the following. It means, so this current A of x, observed by Bethe, Polchinski, and Roybal, it's a flat current. And with flat currents, so the explicit expression I wrote there, so the flat current means that if I have the string world sheet, and if I integrate this current over some loop, if I make some Wilson loop, as was explained already in this conference, so if I define some omega of x, which is the path order exponential of this integral over this current A of x, this is some matrix, right? So as we see there, A is this current there, where I use this set for grading, which we also heard about, and it is made out from this G, so it's an 8 by 8 matrix. So basically it will have 8 eigenvalues, this matrix. Now the fact that the current is flat means that I can place my Wilson loop, I can shift my Wilson loop in time, and the matrix will change by conjugation, but of course the eigenvalues will not change, will be simply rotated. So the set of eigenvalues of this matrix, let me call the eigenvalues exponential of IPJ, as I said it's an 8 by 8 matrix, are conserved, because of course placing them in a different, at a different circle means placing them at a different time, different tau. So I have a set of eigenvalues which are conserved, and the key observation is that they are a function of x. And x is just some complex number, some arbitrary complex number. And no matter the complex number, this current is flat. So I have some conserved charge, which is the eigenvalues of this monodromy, which are conserved for all x. So I have an infinite number of charges, because I can, for example, expand simply as a Taylor series in x. On the other hand, so these quasi-momenta, how do I obtain them? I obtain them by solving some characteristic equation, since they are the eigenvalues of a matrix. And so, from the beginning, this exponential of IP will define some Riemann surface, because they come just from solving some characteristic equation. So this piece, some Riemann surface, which here appear in some trivial case, they will give rise to some H-sheet Riemann surface, which are represented here. So I will have some Riemann surface in the classical equation, and this is the work of Volodya, Kostya, Joe, Niklas, Sakai, and Machakov. I hope I didn't forget anyone. And these Riemann surfaces, in this case they have 8 sheets, they describe then, for each classical solution I have a Riemann surface, and I can describe the classical solutions by these Riemann surfaces. So in these Riemann surfaces they have a set of cuts, they have some cuts which I draw there, and in these cuts, exponential of IP, it's a good quantity in the Riemann surface, as Ecole explained. But of course, since there is exponential for p, I get something like p when you jump. Slash means average above and below the cut. So when I jump through the cut, I can eventually jump by 2 pi n ij. Any question? So this is a classical string motion here. In this picture, I have some classical string. And now I want to consider the semi-classical, I want to consider quantum fluctuations around this classical curve. So what do I do? How do I do it in this language? So what I do, and this was the subject of the first paper in this list, what we do is the following. We say that we have some classical surface, so it corresponds to some cuts. And we add some small cuts, or if you want some poles, or some small cuts, it's the same. For this, I don't care. Some small fluctuations. So how are the fluctuations characterized? The small fluctuations are like a new small cut. Since it is a new cut, as all the cuts, it has its own mode number. So it is characterized by its own n. And then it unites sheet I and sheet j. So the pole, it depends on which sheets I'm uniting and which mode number I'm assigning to the pole. So I add one pole. So this will be one pole. And then for this quantity must obey. So the pole, let me call the position of this pole xn. So where will this pole be located? Well, for the new surface, I am still in the context of this algebraic curve, so still this equation must hold. So let me put p plus delta p and apply this equation in the cuts. So now there are two different sets of cuts, the original cuts and the new cuts. Let me consider this equation on these new cuts. So what do I get? I get trivially that I get a new pole which is located at, so where is the position? I just compute this equation with this expansion at the new position, so I get pi of xn minus pj of xn, where p is the original one, is equal to 2 pi n. So if I add a mode number n of a fluctuation uniting sheets I and j, I know that the position will be located by the solution of this equation, where the original p's are fixed by the classical solution. Okay, and this will be something that I will also use later. So what do? We add this pole, we compute the shift in quasi-momenta, how the quasi-momenta is changed, and we obtain what is the shift in the energy. And what is the shift of the energy? What do we expect physically? Of course, this will be the fluctuation frequencies, n, I, j, which are Frolov, Aritonov, etc., computed. So what are these fluctuation frequencies? So you expand your action around some classical solution. You have some quadratic Lagrangian. And of course, you can, and then the spectrum, the level spacing, is given by the eigenvalues of this quadratic, of the quadratic operator. So what is n and what is ij? What are the physical meaning? N is the mode number. So when you expand around some classical solution, you decompose into Fourier, and you have several possible mode numbers. And n plays the role of mode number. And ij, well, the different ij's correspond to the different polarizations of the possible excitations that I can add. So I can have some classical solution and consider a fermionic excitation, an excitation inside S5, an excitation inside ADS. And this is given by this pair ij. So this is something. This is computing the level spacing of levels close to some classical solution. Now I ask myself a slightly different question, which is, how should I modify this equation in such a way that this equation gets something in the right-hand side, some 1 over square root of lambda correction, square root of lambda, 1 over square root of lambda plays the role of h bar. How should I modify this equation in such a way that when computing the energy which comes out from this equation, I don't obtain the energy of the classical solution, but rather the energy of the classical solution plus the one loop shift, which we know is what? What's one loop shift? It's something like some sum of all the frequencies. So I sum over n, I sum over ij of 1/2 of the frequency, like the ground state, like for the harmonic oscillator is 1/2 of omega. Here I have many frequencies, I have to sum them all. There is a minus in case it's a fermion. And otherwise I should sum all these frequencies. So how should I modify this equation in such a way that when I compute p, I get the classical plus this term here, this one loop shift. And here is how cotangents will appear. So the answer is simple. We know that if we add one excitation to p, we get one fluctuation. So if we want to get all these fluctuations, what should we add to p? Not one fluctuation, but we should add to p. We should add to the right-hand side of the equations all the c of virtual particles. So we should add to the right-hand side of the equations an infinite sum of poles, some of them with plus sign, some of them with minus sign, the fermion ones, and with residue 1/2. So basically, what we do, in order to obtain this equation, we do something that by construction should work. Namely, we change p, we say p goes to p plus some sum of poles. I will specify what this sum of poles is. pi. Each pi I change, I add all possible fluctuations. In other words, these equations will be something like pi minus pj slash will not be equal to pi and ij, but they will get some sum of poles here. And if this sum of poles represents all possible fluctuations, for example, here I drew a couple of them. So I have some fluctuations with plus sign, which are bosons when they cross 2 times, fermionic nodes. And I have fermionic excitations which come with a minus. So if I add the sum of poles to the classical equations, by construction, I should reproduce the one-loop shift. So what is sum of poles? Let me massage a bit this term sum of poles. So sum of poles, which is what we must add. So we already more or less know the answer. The answer must be some cotangents and some integrals of cotangents if we want to match with Bethe ansatze. But here it's completely independent. It's purely quantization of some integrable theory. I represented it as 8 sheets, so of course it's ADS5 cross S5 that I have in mind. But let's see how these cotangents appear quite generically. So I have some sum of poles. What is it? So it is sum over the fluctuate over n and over ij. So let me, of course I can't do it, but let me just replace the sums. I can put some large n and then make the limit. So what are poles? So one pole, so I have the pole, so I have x and ij. Then I will need to know the residue. And what is the residue? The residue, some alpha, like here, alpha was h bar over I, and here is some alpha, which we know what it is. So alpha is 4 pi over square root of lambda x squared over x squared minus 1. This can be seen, for example, from the action variables of the theory. If I know the action variables, I know what it means to add a cut with 1 root or with 2 roots, because I know how to measure the number of roots inside the cut, and this comes, for example, from the papers of Doria and Vicedo. So since I know what to compute the residue, so I know that here I should add this residue here. So this, if I add this to this equation, I obtain a better equation in the sense that it also reproduces the semi-classical spectrum. But you say, okay, it's better, but it is impossible to use. It's highly implicit. I have some function of x, okay, but x, it's a solution of that equation where pi are the original, it's still not usable. So let's massage it a bit. So sum over n, we use some trick which appears in this ADS in a paper by Sakura. So we say that we have some integral over the integers n, and we put some function which has residue, which has one pole at each of the integers. But this is just cotangent. So to sum over n, we can simply integrate with cotangent. And this, of course, is the sum of summing. And here it's exact. I just sum over all integers. I just make an integral over all integers. Okay, this still didn't make my life easier. But now, instead of integrating over n, I will make the change of variables. I go to n to the position xn. So there is a map. If you give me the mode number, I tell you where the root is. So instead of considering n as the variable, I consider xn, the position of the fluctuation, as the variable. So how does, what is the n? Then the n, well, I look at that box, and the n is pi prime minus pj prime over 2 pi dy. And so, all this term, what it becomes? It becomes just simply the integral of alpha of y over x minus y. This is just this part. Then I have dn, pi prime minus pj prime over 2 pi. This comes from dn. Then I have cotange. What is n? N again from the box is just p. Pi minus pj over 2 times dy. So now I have some very explicit correction that I should add to the Bethe equations, which is simply some integral of the quasi-momenta. So now the correct equation should not be quasi-momentum slash minus quasi-momentum slash is equal to integer. It should get this potential on the right-hand side. So, and notice that where are we integrated? We should integrate over the integers n, which means when we go to the x-plane that we should integrate over these positions x. But now, what we should do is, for example, consider these yellow roots. I blow these contours, and if I blow these contours, I am here. I blow this contour, so I go where? I go to this cut here. I go to this cut here, for example, and then x equal plus minus 1 is a special point, as you can see from the expression of the monodromy. I go also to the integral over the unit circle. And therefore, the final result is some integrals over cotangents over the cycles of the original curve, this first two contributions, plus an integral over this cotangent over the unit circle. And then, the integrals over the cotangents, the integrals over the cuts of the Riemann surface, will give exactly the same type of terms that Ecole explained. That is, from the Bethe and ansatze point of view, they come from expansion of these logs, from the nearby roots, which when you expand you get these anomalies, from expansion of the roots and from the mismatches, while the integral over the unit circle can be treated and reproduces precisely the Hernandez-Lopez phase. And so far, everything I did was exact. So I should tell you why exponential corrections appear from the Bethe and ansatze when you consider one loop shift, why it is not exact. So this part here, it's precisely exactly what Collier gets. It's just integral over this over the cycle. So it's precisely the integrals over cotangents. It's exactly what you get from the Bethe and ansatze. When you go over the unit circle, what you do is that you replace cotangents by plus minus I, because close to the unit circle there is this poles, and P typically is of order J. So cotangent is of order 1 plus exponential terms. Is I plus exponential terms. So around the unit circle, you do some exponential corrections. But, so the Hernandez-Lopez phase, so we understand in this formula, so the conclusion is that we can understand how to semi-classically quantize integrable models where we have some classical structure described by Riemann surfaces behind. That in applying this method to the ADS-CFT correspondence, we were able to, on the one hand, check the nested structure of the Bethe and ansatze, which is a very non-trivial check because it's a check of all the equations, not only of the middle node. And we are able to understand in this way where the exponential corrections appear exactly, why there are exponential corrections, mathematically which terms give exponential corrections. And for example, something we would like to do is to understand, as Yannick told, how to understand, I think this could help to understand the exponential corrections around the spinning strings, for example, where it's important to understand exactly where they come from. So for classical solutions, the one loop shift, we'll have exponential corrections, which in this formalism we can precisely track down and eventually then follow its physical origin and hopefully help in the understanding of the wrapping phenomena. Thank you. Without knowing much about the model.
Without knowing much about the model you're talking about.
Yes, exactly.
So do you think this would in principle be possible also for the two-loop correction, or do you have to know more about the action?
No, yeah, of course I have to know more. So what was the input which allowed me to derive the Hernandez-Lopez phase and to fix all this? The input was this connection between fluctuations and one loop shift. So I know that if I compute one fluctuation, if I make a table of the fluctuations, if I want one loop shift, I sum them. But what is the equivalent for two loops? No, for one loop, it's harmonic oscillator. So I make a table and then I sum. For two loops, I compute lots of propagators.
Right, but on the other hand, you might say there's only one model.
Yeah, but for example, if you think of an harmonic oscillator, and if you compute the level spacing of it, so an harmonic oscillator to this order would be the analog of quantum mechanics would be something like alpha x cubed plus beta x4, right? To the next order you need the 2. And if you compute level matching, you can fix them. If you compute the analog not level matching, the level spacing. So from the level spacing of the anharmonic oscillator, you don't fix the parameters of the anharmonic oscillators. So you don't fix the ground state. There is no, you can't know the ground state from the level spacing. Well, here you can. If you know the level spacing, you know the ground state. It's just 1/2 of the level spacing. So of course, we talked about.
More questions? The integrals and the expressions you have, I can understand making sense for the P1 that you're covering. But I mean, surely you need to have the integrals, everything being expressed as integrals on the curve. And I don't see how you make sense of cot pi minus pj. You know, things have to be defined, do they not, for functions on your curve?
So cot p, if you want this function, this function p minus p prime times cot of p minus p prime. So p prime minus p prime times cot of p minus p. It also has its own curve. When you meet the cuts, for example, p3 changes to p2, and so it also has its own curve. So
on your Riemann surface, you cannot subtract. doesn't make sense to talk about the difference between points. It does on P1, but you know, on your curve, you don't have this notion of Pi minus Pj for points on the curve.
Why not?
Oh, but
It's
the
p prime moreover, and it's cotangent, so if I change by integers, it's okay. So maybe, I don't know if this comment helps, but indeed it's integrals. So, for example, p prime, pi minus pj, then here, pi minus pj. If I'm considering a cut ij, this is a very nice function, even simpler than pi minus pj, because this function doesn't even have square root cuts. So, for example, if you want to compute this integral, the contribution for this integral on this type of cuts, you just compute pi residue. It's just the usual cotangent, and this is how you can get the usual finite size projections that one has from Bill Zotz. But then you also have these cuts, which are shared, where one of the extremities is shared by these roots, but the other one is not. And this corresponds to this contribution that Claudia computed with this mismatch. From the Bethe point of view, they have this interpretation of this mismatch.
Probably we have to stop here.